Okay, so now in this second part we're going to carry on and formulate the finite element method using the weighted residual equations. So how do we do that? We need to evaluate the weighted integral equation. So if you come back to what we wrote out earlier in the previous class, we said that we wanted to evaluate the weighting function given by this here. So the weighting function had two terms. Has this surface integral where we have the derivative of the weighting function with respect to x, the derivative of the trial function with respect to x, the derivative of the weighting function with respect to y, and the derivative of the trial function with respect to y. And that's all integrated over the surface area of the problem. Okay? And then the second term was the weighting function times the current density. And so this whole integration, both of these integration terms, we want to become equal to 0 to minimize. Now we previously evaluated what the trial function is for a single triangle, and we got out equation 11 here. Okay, so now if we look at the weighting function here, we've got to evaluate the derivative of the magnetic vector potential with respect to x and the derivative of the magnetic vector potential with respect to y. Now, if you recall, that actually gives us if you take the derivatives of the vector potential with respect to the spatial directions, that actually gives you the magnetic flux density. So I'll actually write this out in terms of, I'll write out the magnetic vector potential derivatives as partial derivatives in terms of the magnetic flux density. So to obtain Bx and By, recall that the B magnetic flux density is equal to the curl of the magnetic vector potential. So in this 2D problem, we only have to evaluate the Z term. The magnetic vector potential only has a Z term. So then, evaluating this, we can find that Bx, so if we evaluate x, we're going to get, whoops, that should be a y there. If we evaluate x, we're going to get del A, del y. And I'm going to call that 22. And if we evaluate the by, we're going to get, so by, it's going to have a negative sign in front of it, and we're going to have del A, del x, like that. Okay? So then we know what these trial functions are. The trial function for A is given by 11. Now we also wrote it out explicitly. We solved for A1, A2 and A3, and when we did that we got out equation 17 here. Okay, so 17 is written in terms of basically a constant terms, first one. The second term is a function of x, and the third term is a function of y. So if we take the derivative of this trial function with respect to x and y, that will give us the bx and the by values. So bx is the derivative of a with respect to y. So if we substitute 17 into 22, that will then give us bx is equal to, so we're going to take the derivative with respect to y, so we just get out 1 over 2 delta is equal to ai ri plus aj rj plus ak rk. Okay, so now then we could actually write this in a matrix form, and that would be then ri rj rk is multiplied by ai aj and okay, like that. Okay, now I'm going to call that, so this is 23. I'll call this 24. So we can get out the by by substituting in 17 into 23. And when we do that, so if we substitute, we've got 17, we put 17 into 23, so 17 into 23, that will give us the by trial function. So that will give us 1 over 2 delta times ai qi plus aj qj plus ak qk, and then we can rewrite that in terms of 1 over 2 delta qi qj qk as a matrix, and times ai aj ak. I'll call that 25. So now that will give us the by. Okay. So that's so now if we look at our weighting function, we've evaluated what the derivative of a with respect to x and a with respect to y is. So now we only have to evaluate the derivative of weighting function with respect to x and the weighting function with respect to y. Okay, so I'm going to call this equation 26. Okay, so now we just have to evaluate what these weighting function terms are. All right, now this is where the theory that we talked about before comes in. So what we're going to do with the weighting functions in this is that we're going to choose the weighting functions to be equal to the basis functions. And remember what that is? That is the Galerkin method. If we choose the weighting function equal to the basis function. Now, from our derivation of the trial function, we got out what the basis functions were. Remember, they are Ni, Nj, and Nk. So let's now write out what the weighting functions are and then take the derivative of them with respect to x and y, and that will give us these two terms here, and then we can completely formulate our solution. Okay, so let's do that step now. So we have that the trial function is written in terms of ni plus nj actually I think I'll erase this now. Nj aj plus nk ak. Okay, so we could write this in a matrix form. So then we'd have ai, aj, ak, okay, times ni, nj, nk, like that. Now this second term here is the basis function. The first term here is the known values at the nodes of the triangle. So that would be just numbers. This is a basis function which would is a function of x and y. So this is the basis function. Okay, and I'll call this 27. So the Galerkin method, the weighting function is equal to the basis function. So in that case, so for the Galerkin method, the weighting function equals basis function. So then from 27 we have that the weighting function is equal to ni, nj, nk. So that's pi, qi, x, ri, y. Now I'm writing out, I'm expanding out what ni, nj, and nk are. So the nj is equal to pj, qj, x. This should have pluses here. Qj, x plus rjy, and then nk is equal to pk plus qkx plus rky, and that's all multiplied by 1 over 2 delta. Now in order to evaluate our weighting function, this functional here, we've got to take the derivative of the weighting function with respect to x and the weighting function with respect to y. So this is our weighting function here, equal to our basis function. So let's take the derivative with respect to x and y and see what we get. So the derivative of the weighting function with respect to x So in that case, there's just the Q terms left. So we get Qi, Qj, Qk times 1 over 2 delta. That's 28. And then the derivative of the weighting function with respect to y, that gives Ri, Rj, Rk, and that's 29. Okay, so now we've got these derivative terms, and we've also got the derivative terms of the vector potential, so we can put it all together. So let's evaluate the first term here in the weighting equation. So we've got the derivative of the weighting function with respect to x, the derivative of the magnetic vector potential with respect to x. So that's equations 28 here and 25. So let's multiply those two together. So let's evaluate first term in 26. So using 28 and 25 gives, so we have del W, del X, del A, del X. So del W, del X is the 28. So we have we've got 1 over 2 delta here, and we've got 1 over 2 delta here, so multiplying those two together gives 1 over 4 delta squared. So we have 1 over 4 delta squared. Then we have Qi, Qj, Qk, and then that's multiplied by so that's the 28, and now we've got to multiply that by the derivative del A del X. So this is from the del W del X term. So we get Qi, Qj, Qk times Ai, Aj, Ak. Okay, so then we can expand this out, and we are left with 1 over 4 delta squared. Now this is going to become a 3 by 3. So we go across and then down, cross and then down, cross and then down for the top term. So we get Qi squared, Qi, Qj, Qi, Qk. And then the second term is Qj, Qi, Qj squared, Qj, Qk. And then the third term is Qk, Qi, Qk, Qj, Qk squared. And that's multiplied by Ai, Aj, Ak, like that. Okay, so that's equation 20. Oh, sorry, 30. Now we've evaluated the first term in 26. Now let's evaluate the second term. So using 29, 24, second term in 26 will be, so we have del W, del Y, del A, del Y. So again, we get 1/4 delta squared, and then the del W, del Y, we get Ri, Rj, Rk. So that is Ri, Rj, Rk, right? And then the del A, del Y, if I erase that now. Let me write that out. So that's going to be, actually that's this one here, right? That's the Bx. So we get times, so this is from 29, and the next term is from 24. So we have Ri, Rj, Rk multiplied by Ai, Aj, Ak, like that. So this can then be multiplied through. Oh, sorry, that should be a multiplication there. So we get 1/4 delta squared times I squared Ri, Rj, Ri, Rk, and then the second row is Rj, Ri, Rj squared, Rj, Rk, and then the third term is Rk, Ri, Rk, Rj, and Rk squared. Like that, and then that's all multiplied by Ia, Aj, and Ak. Phew. Okay. So now we've finally evaluated the two differential terms. Now you may be starting to get worried that we've still got these pesky integrals here, okay? But turns out that it's not so big a deal. So if we look at what is inside the matrices, okay, so what are these Qis, Qjs, and Qks here? Now remember, these are the coordinates for the location of the triangle. They are not functions, therefore, of x or y. They're just positions, known positions of the triangle. So they're just numbers, location numbers for that triangle. Similarly, for the second term, they're in terms of Ri, Rj, and Rk. These are also position points for the nodes of the triangle. So neither of these two terms has anything in it that is a function of x and y. So that makes the integration very easy, because none of this has any x and y in it. So we can actually take out these partial derivatives outside of the triangle for the first term. So let me write that. Note, R and Q values in matrices are functions of coordinate points. They are not functions of x and y. Thus, we may move area of integral. We must, thus we may move terms outside of integral. Okay, so what I mean is we have 1 over mu, and evaluating the double integral, del w, del x, del a, del x plus del w, del y, del a, del y. So this first term just becomes, so we can move all this out. So we just have del w, del x, del a, del y, plus del w, del y, del a, del y, and that's all now outside of the integral. So what's left is 1. And if we evaluate this integral over that one triangle, we get the area of a triangle. So this is 32. So this becomes area of triangle. Right? So that's nice. So that's just equal to delta. Is equal to delta in this example, and I'll call that 33. So now we can substitute the two terms, 30 and 31, into here and add them, and that will then give us the solution, matrix solution for the first term.